This is the conventional strain energies of cyclopropylborane, borane, boratane, the diborotanes, borylane, the diborolanes, boronane, and the diboronanes. So what is ring strain? Well, the term strain was first introduced into chemistry by a man named Adolf von Baeyer in 1885, and he described ring strain as any deviations from tetrahedral directions of bonds in cyclic carbon compounds, and this type of strain is known as Baeyer strain. It's also known as bond angle strain. But in addition to this bond angle strain, there are other types of strain that cyclic carbon compounds can undergo. So the first type is stretching or compression strain, in which bonds are longer or shorter than usual. There's Pitzer strain, which is bond eclipsing strain, and there is Dunitz-Shoemaker strain, which is strain that results from the compression of van der Waals radii. So why is ring strain even important? Well, ring strain can be used to explain or sort of rationalize instability and reactivity of small cyclic organic compounds. And these small cyclic organic compounds that are strained have the ability to interact with pi systems, which is intriguing. And also these strained cyclic systems might aid in a search for high energy fuels. Most ring strain studies focus on cyclopropane and cyclobutane. And even though cyclopropane has additional Baeyer strain, the conventional strain energies of these systems are very similar. They're usually reported to lie within 1 to 2 kilocalories per mole of each other. This similarity in their conventional strain energies is because of the stabilizing effect from sigma delocalization in cyclopropane. And so we have previously investigated the replacement of carbon with nitrogen, oxygen, phosphorus, and silicon, and observed how the conventional strain energy of these systems changes. And now we want to investigate how replacing carbon with an electron-deficient boron will affect the conventional strain energy of these systems. Also in our study, we want to investigate this strain release-driven expansion of cyclopropylborane. So in 2012, Rubina and Rubin reported spectroscopic identification of boratane through a strain release-driven expansion of cyclopropylborane. And if we compute the conventional strain energies of boratane and cyclopropylborane, we will be able to confirm or also maybe deny that this expansion of cyclopropylborane is in fact a strain release-driven expansion and that it's not due to some other factor that we're not sure of yet. In order to experimentally determine the strain energies of a cyclic hydrocarbon, you first would start by measuring the standard enthalpy of combustion for a single CH2 molecule. And this is done by measuring the difference between large sequential straight chain systems. And this value is quite constant at 157.44 kilocalories per mole. Then you would measure the difference between N times the above value and an N-carbon cyclic system, and the resulting number would be the conventional strain energy because these energies are measured on actual systems. So the experimental strain energy of cyclopropane is 27.5 kilocalories per mole, and the experimental strain energy of cyclobutane is 26.3 kilocalories per mole. In order to determine these strain energies computationally, we use something called the model reaction approach. So we use isodesmic, homodesmotic, and hyperhomodesmotic reaction models to do this, and we are calculating the change in internal energy. So for a straight chain hydrocarbon, these reaction models are measuring the internal energy, which is essentially zero because there's nothing unique going on. We're just breaking the same bonds that we form on the other side of the reaction. But when you add a ring, you now have something sort of unique. And so now when we calculate the change in internal energy, we can equate that change in internal energy to the measure in the ring strain. So this is the isodesmic reaction model in which both the number and types of bonds are conserved. And so in this example reaction with pentane, we can see that there are 4 carbon-to-carbon bonds and 24 carbon-to-hydrogen bonds on both sides of the reaction. Next is the homodesmotic reaction model, and these are isodesmic reactions that also conserve the valence environment around each atom. So in this example reaction, we can see that there are 3 CH2 groups bonded only to other carbons and 6 methyl groups bonded only to another carbon on both sides of the reaction. Lastly, we have the hyperhomodesmotic reaction model. So this is a homodesmotic reaction that conserves the valence environment around each set of 2 bonded atoms. And just like the other 2 reaction models, we can see that each of those things are conserved on both sides of this reaction. Now for the computational details. So for every reactant and every product in each of our model reactions for every compound that we researched, optimized geometries and corresponding vibrational frequencies were computed using SCF, B3-lip, MO6, 2X, and MP2 levels of theory with the correlation consistent double zeta, triple zeta, and quadruple zeta basis sets. And electronic energies with 0-point vibrational energy corrections were used to then compute the change in energy and therefore the conventional strain energy for each of our model reactions. Computations involving the MP2 level of theory and the triple zeta basis set utilizing the homodesmotic models gives conventional strain energies for cyclopropane and cyclobutane to be 27.3 and 26.0 kilocalories per mole respectively. And using the same level of theory and the same basis set for the hyperhomodesmotic models gives us 27.8 and 26.8 kilocalories per mole respectively. So if you take the average of those results, you get 27.6 kilocalories per mole for cyclopropane and 26.4 kilocalories per mole for cyclobutane. And from these results, we can see that these values using the MP2 level of theory and the triple zeta basis set consistently agree, which proves that these computations are capable of yielding reliable results for our research. These are our computed conventional strain energies in kilocalories per mole for borane, boratane, 1,2-diborotane, and 1,3-diborotane. Here we have results for cyclopropylborane, borylane, 1,2-diborylane, and 1,3-diborylane. And lastly, we have results for boronane, 1,2-diboronane, 1,3-diboronane, and 1,4-diboronane. And now for our conclusions. So first we can conclude that the isodesmic results are mostly unreliable because the results don't agree as well or as consistently as the results that we get from utilizing the homodesmotic or hyperhomodesmotic reaction models. We can see from the results that boronane is the least strained compound that we considered, and borane is the most strained compound that we considered. And we can also see that boratane and 1,3-diborotane have similar conventional strain energies to cyclobutane, but 1,2-diborotane is more strained. A couple more conclusions. With the exception of 1,2-diboronane, we can conclude that isomers with 2 adjacent boron atoms are always more strained than those in which the borons are separated by a carbon. So, for example, we can look at 1,2-diborylane and 1,3-diborylane. 1,2-diborylane has a much higher strain energy than 1,3-diborylane because its 2 borons are not separated by a carbon. And lastly, we can conclude that cyclopropylborane is less strained than cyclopropane or boratane, which gives us an answer to our previous question. So obviously the expansion of cyclopropylborane is not driven by strain release. Lastly, I would like to thank Dr. David Majors, the Mississippi College Computational Chemistry Group, and Mississippi College Catalysts, the Department of Chemistry and Biochemistry Alumni Support Group.